This is a direct instruction for February 29th. And we'll cover various topics. We'll start off with a rectangular coordinate system. Rectangular coordinate system looks like this. Where this is your x-axis and this is your y-axis. Now you have the place where they meet. This is called the origin. And the rectangular coordinate system splits these into quadrants. This quadrant right here is our first quadrant. This is our second quadrant, third quadrant, and fourth quadrant. And it's kind of, again, it's not quite what you might think since it's counterclockwise. Now, quadrants don't have a whole lot of purpose in college algebra. We use them a little bit, but they're used quite a bit in trig if you want to take that class. Now, the next topic is plotting points. A point looks like this example. You have parentheses around it, and then you have a number, comma, another number. This first number is the x part of our point. And this second number is the y part of our point. So if we were to go and plot points, here's our x-axis. We got 1, 2, 3, 4, 5, and so on. As I go this direction, it's -1, -2, -3, and so on. And then as we go up, it's positive. So we've got 1, 2, and 3. So if I was plotting point 2, 3, we said our x part is 2. So I go to the, on my x-axis where it's 2, and I draw a vertical line. We set our y as 3, so we'll go to where 3 is on our y-axis, and we draw a horizontal line. Now where they intersect is going to be where we put a point if we were to plot this point. So this point would be 2, 3. Most of the time you don't actually draw those lines. You just visually look at it and see where x is 2 and y is 3, and that's where you drop a point. Kind of the same idea as that game Battleship. I forget what's across the bottom, where there's letters and then there's numbers, and you say A5 and so forth. So same principle. You got to have some kind of coordinate system to be able to map things out. Now let's look at a negative point. Oftentimes you'll see letters put in front of them, as in this example. So we want to plot this point, -2, -4. Well, I'll go to where x is equal to -2, because remember this is our x part, and this is our y part. So here's x equals -2, and I'll go to where y is -4, which is right down here. And where they would intersect, if I drew lines, would be right there. So that'd be our point -2, -4. And you put a letter by it if you're using this notation. Now if one of your values is 0, in this case 3, 3, 0, remember this is your x and this is your y. So we go to 3, 0, x is equal to 3, and if this is y is equal to 1, this is y is equal to -1, y is equal to 0, is right here, which is our x-axis. So this point would be on our x-axis, and I'd label that as B. If we had another example where we had 0, 5, again, this is our x, and this is our y. So we'll go to where x is equal to 0. That's -1, and this is x equals 1. X equals 0 is right here. So 0, 5 would be right up there. Now I'll put the letter next to it. So that's plotting points. Now we're going to take a look at graphing linear equations by plotting points. So let me clear this off. Say we got y is equal to 2x minus 3. And let me actually highlight one we're working on. Of course, that didn't work very well with my pen. Now we're going to build something called a t-chart. We have a x column and a y column. In our x column, we're going to list some x values. Your choice what numbers to pick. I'm going to pick -1, 0, and 1. You could have chose 0, 1, and 2. You can pick any x value. You probably want to keep them fairly small, fairly centered around the origin. If you pick x equals 1 million, then you're going to have to really kind of skew your graph to see it. Now after we pick these x values, our first one is we got x is equal to -1. So we're going to plug x equals -1 into our original problem. So we got y is equal to 2x minus 3. So we got 2 times -1 minus 3. 2 times -1 is -2 minus 3, or y is equal to -5. Now this is going to be our point, our ordered pair, -1, -5. And then we'll plug in our second x value, 0. And we'll plug that into our original problem. So we're going to have y is equal to 2 times 0 minus 3. 2 times 0 is 0, and that gives us y is equal to -3. And then our last one, x is equal to 1. We're going to plug 1 in for the x. So we've got y is equal to 2 times 1 minus 3. 2 times 1 is 2 minus 3, which gives us -1. And this is our t-chart. Now this whole chapter is centered around, at first, around linear equations. But they do throw other items in here. You're not limited to just y is equal to 2x minus 3. I think one of the problems I saw involved an absolute value. And so the same concept holds true no matter what you're working with right here. Now normally all we would need is 2 points in order to graph. The third one is a point that helps us check our math. See, make sure I didn't make a basic math error somewhere here. Now -1, -5 would be right there. 0, -3 would be right there, and 1, -1 would be right there. Then after you plot those points, you just draw a line through them, as straight as I can draw it, and that would be your graph. Now it doesn't have to be solved for y in this case. You just go through and solve whatever it looks like. For example, if I had 2x plus 3y is equal to 5, and I'm wanting to build my t-chart, I'm going to choose negative 1, 0, and 1. Now we're going to see that this is not going to come out perfect, but that's okay. So if I plug in x equals negative 1, then this 2x plus 3y is equal to 5. We got 2 times negative 1 plus 3y is equal to 5. 2 times negative 1 is negative 2 plus 3y equals 5. And remember, solving equations, well, that's what this amounts to. Get rid of parentheses, get rid of fractions, get everything with a y on one side, numbers on the other side. So I take negative 2 over. Becomes a positive 2. We get 3y is equal to 7, or y is equal to 7/3. Now 7/3 is real hard to work with when you're trying to plot points. It's better to put it in decimal form. And this is, if you've ever taken a look at 1/3, we know it's going to repeat forever. This is 7/3, but same idea. So if we do 7 divided by 3, then we get this. How many decimal places? Probably 1's good enough. If you're so good at graphing you can do more than 1 decimal point, then I'm impressed. Then we'll plug in our second x value, x equals 0. So we got 2 times 0 plus 3y is equal to 5. 2 times 0 drops away. We got 3y is equal to 5. Divide both sides by 3. And we get y is equal to 5/3. Again, 5/3 is kind of a difficult one to work with. But if we put it in decimal, we'll be able to plot the point better. That gives us 1.7, rounding to 1 decimal place. And then our last one, x is equal to 1. We'll plug 1 in for the x. So I got 2 times 1 plus 3y is equal to 5. And this one looks like it's actually going to come out nice. 2 times 1 is 2 plus 3y is equal to 5. Take the 2, move it to the right side. Although I'm not saying it, we're just going through solving linear equations. Get rid of parentheses, get rid of fractions, get everything with y on one side, numbers on the other side, or constant terms. 5 minus 2 is 3. And then last step, divide both sides by a number in front of your y. So divide both sides by 3. And we get y is equal to 1. Well, now if we go to plot these points, we got negative 1, 2.3. So negative 1, 2.3. I had a professor at Wichita State one time. He said while you're plotting points, if you're not quite sure if you got it in quite the right place, just make your dot a little bit bigger, and you got yourself covered. He called it the big dot theorem. And because we're just sketching, and he's right, you don't spend a whole lot of time on it. 0, 1.7, it'd be about right there. And then 1, 1, be about right there. And then you draw a line through them, and that would give you your graph. Now that is graphing linear equations by plotting points. There's another method that involves finding the intercepts. So let's take a look at how to find the intercepts. And I thought I had Word up, but I don't, so I'm going to bring it up. Now for our intercepts. The x-intercept is where the graph touches or crosses the x-axis. And the y-intercept is where the graph touches or crosses the y-axis. Now, graphing by using intercepts, for lines anyway, is a popular technique because it's pretty simple to find the intercepts. Finding the x-intercept, you plug 0 in for y and solve. It's always the same. Whatever intercept you're trying to find, you always plug 0 into the other variable. So finding the y-intercept, you plug 0 in for x and solve. So let's take a look at an example of finding the intercepts, and then we'll take a look at graphing using intercepts. Now, finding intercepts by themselves would be, let me clear off my tablet. Okay. We're going to find the intercepts of 3x plus 8y is equal to 9. Now for our x-intercept. Finding the x-intercept, you plug 0 in for y and solve. So we're going to take our 3x plus 8y equals 9, and we'll put 0 in for y. And then we want to solve. Well, 8 times 0 is 0, so that drops away. And this is just a linear equation. Get rid of parentheses, get rid of fractions, get everything with x on one side, numbers on the other side. Divide both sides by a number in front of your x. So we'll divide both sides by 3. Now when we do that, those 3's cancel. And we got x is equal to 3. Now, point-wise, this is written as 3, 0. And if you're wondering why does the 0 go there, well, remember our instructions. Plug 0 in for y. And this is the y part of our point. Now to find the y-intercept, we plug 0 in for x and solve. So we're going to go back to our original problem, and we'll plug 0 in for x. So I got 3 times 0 plus 8y is equal to 9. 3 times 0 is 0, so it drops away, and we got 8y is equal to 9. When you're finding intercepts, it will always drop away like that. Then we're going to divide both sides by 8 to get to y by itself. I'm going to do that, those 8's cancel. And we get y is equal to 9/8. Now remember what we did for the y-intercept. We plugged 0 in for x. So this point would be 0, 9/8. And those would be our intercepts. Now sometimes when you get into a little bit problems that are more difficult in terms of graphing, the intercepts is a little piece of the puzzle. For example, if you do want to take calculus, the intercepts by themselves won't give you the graph, but they'll give you an important piece to the puzzle. And there'll be other things you'd find, like you'd find increasing and decreasing intervals, you'd find mins and maxes, and all of those different components help give you the true picture of what the graph looks like. But let's take a look at graphing one of these now, and see why some people like graphing using intercepts. We're going to graph 4x plus 3y is equal to 12 using intercepts. Well, we'll first find our intercepts. For our x-intercept, we'll plug 0 in for the other variable, so we'll plug 0 in for y. So I got 4x plus 3 times 0 is equal to 12. 3 times 0 drops away, so we got 4x is equal to 12. And to get the x by itself, we're going to divide both sides by 4. And those 4's cancel. And we get x is equal to 3. So this point would be 3, 0. Now for our y-intercept. Going to always plug 0 into the other variable, so plug 0 in for x. So I got 4 times 0 plus 3y is equal to 12. 4 times 0 drops away. We got 3y is equal to 12. And then divide both sides by 3. When we do that, those 3 is going to cancel. And 12 divided by 3 is 4. So this point would be 0, 4. Now for graphing, now that we got those 2 points, 3, 0 would be right here. 0, 4 would be right here. And then I draw a line through them. Should be a straight line. But that's about as good as I can do by freehand. I wish there was a straight line tool on this. But again, that should be a straight line. And you see that the math was a lot easier than what we did when we built the t-chart. So that's graphing using intercepts. Now later on, when we look at other graphs, the intercepts may not be enough. Even for a line, if I find my intercepts, and the only intercept I have is what goes through the origin, well, we know we at least have to have 2 points to sketch a line. And you may be wondering, where's the third point you referred to? Usually the math is so simple on the intercepts because part of it drops away that you don't need to find a third point. You can just be on the safe side. But if your only intercept is in this 1 point, you have no clue what it looks like. It might be a line. Might look like that, or it might look like this. Or it could even be what's called a parabola. Could be that. So the intercepts, in some cases, gives us a piece of the puzzle, but doesn't give us the entire picture. Now we're going to take a go away from lines for a little bit, and we're going to talk about functions, and then we'll go back to looking at slope. Because functions are introduced here, so we can then talk about a linear function. Now a function says for every x, there is only one y. For every, let me see if I can get this right. For every car that is running, there is only one driver at any given time. If the car is not running, of course, you could have various people that might potentially be the driver at that point. Now, this is a very hard definition to use unless you're dealing with points. So let's look at some examples. I'm going to give you a shorter or easier definition that will shorten problems down. But first, let's look at some points. We're wondering if the following is a function or not. Then we got the points 1, 2, 3, 4, and 5, 6. What we're going to do is we're going to create a mapping. And what we're going to do is we're going to write down our x values going from smallest to largest, not repeating any. So our x values of our points is 1, 3, 5. So I got 1, 3, 5. And then we're going to write down our y values going from smallest to largest, not repeating any. So 2, 4, 6. Now this is called a relation. A relation is where you have some kind of mapping, that this is related to this. And this is a mapping of a point, where it maps the x to the y part. So I'm going to draw a line between the 1 and 2. Now this one maps 3 to 4. And this one maps 5 to 6. Now our definition says, for every x there is only one y, which means you can only have one line coming out of each x value, which is true in this problem, so this would be a function. Now I'm going to show you one that is not a function. Say we had 1, 7, we had 1, 9, and we have 2, 1. Again, for our x values, we're going to write them from smallest to largest, not repeating any. I got 1, 1, 2, so I'm going to have 1 and 2. Then my y values, I'm going to write them from smallest to largest, not repeating any. I got 7, 9, 1, so I got 1, 7, 9. Now this first point maps 1 to 7, so I draw a line between them. This next one maps 1 to 9, so I draw a line between them. And this one maps 2 to 1, so I draw a line between them. Now I said for every x there's only one y. That's our definition of a function. But we see for this particular x value, we got two lines coming out of it. It's being mapped to 7 and it's being mapped to 9. Since we have two lines coming out of it, then this is not a function. Now that's a graphical view of it. There's an abstract shortcut for it. And it says if your x values repeat, it's not a function. This is a shortcut determining if points are a function. If the x values repeat, then it is not a function. If I come back to my first problem here, I got 1, 3, 5. If the x values repeat, it is not a function. Since the x values did not repeat, then this one was fine. This one was a function. But in our second example, see how we have 1 here and 1 here? Right away the x values repeated. If the x values repeat, then it is not a function. So that's why it would be not a function. So you can do it either way. You can do a mapping to see it, or if you want to use that shortcut, that'll handle points. Now where this becomes tedious and hard to work with is if you had a problem look like this. We got y to the fifth minus y plus the absolute value of x is equal to 7x plus y to the third. To actually use that definition, what we'd do is we'd have to plug in x values. So plug in x equals 1 and then solve for y and see if it gives me 2 or more different y values. Plug in x equals 2, see if it gives us 2 or more different y values. Plug in x equals 3, see if it gives us 2 or more different y values, and so on. I always give this example in class. I ask if there's any runners, and usually I get one person that is a runner of some sort, and I'll ask him if he runs 1 foot or if she runs 1 foot. And they look at me kind of weird. It's like, yeah, and then I say, can you run 2 feet? And they still look at me kind of weird, and they say yes. And I say, can you run 5,280 1 mile? And they say yeah. And 10,560 2 miles, and they say yes. And then I say, at some point, that person is going to fall over. The fact that they can run the first 100,000 feet doesn't mean that it's going to work all the time. Well, the same idea applies in this. We could sit here and plug in 100,000 x values and think everything's okay, but then the very next one it would fail on. Well, this is not a very good technique to determine if something's a function or not. There's an easier definition, and it says and this is easier definition of a function, I should say. If you have one of the following, then it is not a function. If you have y to an even power, then it's not a function. If you have the absolute value of y, it's not a function. If you got the plus or minus symbol, it's not a function. Or if you got x is equal to a number. And what I mean by that is you'd have like something like x is equal to 3. You wouldn't have anything else in the problem. You just have x equals 3. Now these are the popular ones that we see in college algebra. You go on to trig and calculus and you build onto this list. But if we look at this problem I just had up here, we said we can't have y to an even power. Well, we have y to an odd power. That's fine. Now here we have a y, and we know that's y to the first, so that's fine. We just can't have y to an even power. These are the items we cannot have. Absolute value of x. Well, that's okay. We said we can't have absolute value of y. We didn't say anything about x to a power, so that's fine. And over here we got y to an odd power, so that's fine. So this one, using our easier definition, this would be a function. Where's that used at in this class? Well, there's some definitions in the book that say this only applies if it's a function. And so a tricky problem thrown in might be one that's not a function. They're asking you to calculate whatever math topic. Go ahead and clear that off. And then we'll talk about function notation. Now, function notation. Some people really get hung up on function notation. It's a fairly simple idea. One is to give it a name. That's its first purpose. Same as when we name a child. You could name them all the same name, but that might be kind of difficult. So you give them unique names, so you can easily refer to them. Let's say we had this, y is equal to 3x plus 1. And I had y is equal to 5x minus 2. If I told you to graph y, your question would be, well, which one? We got two y's. So what we do is we give it a name. We don't give it a name like Bill or Bob or anything like that. But you say this right here, that's its name. And this one would be named perhaps this. Now how you read this is read as f of x. So that's read as f of x is equal to 3x plus 1. We even get lazier in math. We just refer to it as f. Over here, this is read as g of x. And we even get lazier in math, and we refer to it as g. Now, these letters actually mean something when you go on to other classes. If you go on and take a business calc class of some sort, you'll deal with c of x, c for cost function, uppercase p, p for profit, lowercase p, p for price or demand function, r of x, r for revenue, and so forth. For algebra, it's pretty much going to be generic letters we pick. It doesn't matter what letter you pick. You probably don't want to pick x. X of x wouldn't be appropriate. But that's the first purpose of function notation. Now these are interchangeable. This is given it a name, but if you want to graph it, you can replace the f of x with y, and you can always do that. Or if you got y is equal to 3x plus 1 and you want to give it a name, you can automatically throw function notation in there. Now it's got a second purpose, and this is to shorten writing. And let me show this with an example. We had problems back in previous math courses said evaluate y is equal to 3x minus 1 for y when x is equal to 5. And how we'd solve this, and yeah, I have room I think, is we would say y is equal to 3x minus 1. We would replace the x with 5. And then 3 times 5 is 15 minus 1, or y is equal to 14. Well, instead of writing all those words down, we could say f of x is equal to 3x minus 1 and say find f of 5. That says the same thing as all these words over here. So that's the second purpose of function notation, is to shorten writing. Now it's worked the same way. To find f of 5, we go through and we replace our x with parentheses, and then we plug 5 in. So then f of 5 is equal to 15 minus 1. F of 5 is equal to 14. Now remember, this is interchangeable. This f of 5 here we could equally just replace with y at any point. So this is really saying when we see f of 5, that's saying y is equal to 14. So again, shortens writing. This specifically is called evaluating a function. And I'm going to write the steps down here for evaluating a function, and then we'll look at an example. So evaluating a function. Step 1 is replace all the variables with sets of parentheses. Step 2, plug in whatever we are evaluating for into the parentheses. And step 3 is simplify. Simplify is probably the most complex instruction there is in mathematics. It probably means 500 different things. Get rid of parentheses, simplify fractions, add numbers, lots of different meanings to it. Now let's take a look at an example of evaluating a function. We got f of x is equal to 5x minus 2, and we want to find f of 4. Okay, so first off, this really vague item I wrote here, whatever we are evaluating for. Whatever is inside the parentheses right here is going to be whatever we are evaluating for. It's not always going to be a number, it can be anything. And that's what I'll show in the second example. Okay, so let's find f of 4. Step 1, replace all variables with sets of parentheses. So everywhere I have an x, I'll put in a set of parentheses. That's step 1. Then in step 2, and sometimes people do step 1 and step 2 on the same line. They don't write it again. Step 2 says plug in whatever we're evaluating for into the parentheses. Now whatever is inside the parentheses right here is automatically what you're going to put in right here. So I'll put a 4 in there. And then step 3 would be to simplify. Simplify when you're dealing with numbers basically means order of operations. Please excuse my dear Aunt Sally. Please do what's inside the parentheses. There's nothing to do inside the parentheses. Excuse exponents, nothing. My dear, multiplication division. 5 times 4 would give us 20. I'll bring down to minus 2. And then Aunt Sally, addition, subtraction. 20 minus 2 is 18. Now, it does not have to be a number. In this case, we want to find f of x minus 1. Well, it's still the exact same steps. That never changes. Step 1. Replace all the variables with sets of parentheses. So go into our original function, and everywhere we have an x, we'll put in a set of parentheses. And I'll go ahead and do step 1 and step 2 in the same line so you see it. Step 2 says plug in whatever we're evaluating for into the parentheses. Again, whatever's inside the parentheses right here will always be what we plug in right over here. So I'll plug in x minus 1. And then step 3, we want to simplify. In this case, we'll use the distributor property. I'll take 5 times x is 5x. 5 times negative 1 is negative 5. Bring down to minus 2, which ends up giving us 5x minus 7. And that would be our answer. Now, one more example of evaluating a function. Let me show you one that has something a little bit more complex. Say we got f of x is equal to x squared minus 7x plus 5. And we want to find f of negative 2. I try to be random when I make these up, but I guess I am different than that. So let's find this. Step 1. Replace all the variables with sets of parentheses. So we'll go to our original function, the x squared minus 7x plus 5, and everywhere I have an x, I'll replace it with a set of parentheses. Now notice everything else was remaining exactly the same. Second power, the minus 7, the plus 5. All I did is replace the x's with parentheses. Step 2. Plug in whatever we're evaluating for into the parentheses. So whatever's inside the parentheses right here is automatically what we'll put into both of these parentheses. So I'll put in negative 2 here and negative 2 here. And then step 3, we want to simplify. So we go to order of operations. Please do what's inside the parentheses. Nothing do inside the parentheses. Excuse exponents. Well, I have an exponent, negative 2 squared. That gives us a positive 4. My dear, multiplication and division. Well, we have negative 7 times negative 2. That gives us a positive 14. Aunt Sally, add and subtract. 4 plus 14 is 18, plus 5, which gives us 23. And that's our answer. And that's evaluating functions. Now, as always, if you have any questions on any of this, be sure to ask. Now we're going back to lines now, and then we're going to build it into looking at a linear function, which is nothing exciting except we throw the function notation in there. Now, first thing we'll talk about is slope. And I haven't read the textbook, to be honest, so I couldn't tell you how they describe slope. Most people describe it in a manner that I really don't like. Slope is always represented by little m. And it's the change in y over the change in x. You may have heard it referred to as rise and run. Horrible way to focus on it. It gets you thinking distance. And it's much more than that. I am not to do an advertisement for Dr. Pepper, but I bought this last weekend. So I had a change in finance over change in time. I bought it because it increases my alertness. So I have a change in alertness over change in time. It also makes me happy. So change in happiness over change in time. You can put anything in for these variables. If you're looking at your miles per gallon, You could have change in miles over change in gallons. If you're in business, change in profit over change in time, over change in years. Change in costs over change in weeks. So you can put anything here. Now this encompasses so much of our lives that if you go on and take a calculus class, half the class is basically studying this concept here. Let me give you an example. Let's say in 2012 the profit was $10 million. And I always ask this in class. I say, is this good? And usually the first reactions, people nod, and it's like, well, yeah, that's fantastic. You paid all of your costs, and you got the $10 million profit. Well, how about if in 2011 your profit was $1 billion? Well, now it's horrible. Your company's going under. Went from $1 billion profit to $10 million. Well, how about if in the previous year you went from $1 to $10 million? Well, now it's fantastic. Get some new investors and expand your company. You're doing great. Well, how about if this was 9,999,999 and you went to 10 million? Is it good now? Well, it's probably questionable. If you're selling toilet paper, probably that's about right. People don't change their toilet paper very much, so sales are probably very consistent, profits very consistent. If this is technology, this could mean that your profits leveling off as the new technology is coming out, and it'll make your previous technology obsolete. One of the companies I worked at, they would sell companies. This was Coke Industries. They're a large company that consists of a bunch of smaller companies, and they would sell companies that are making money. Now, these smaller companies they're selling are still not very small. Now, I worked on the financial side, so I could see this, and I asked an accountant one time. I said, well, why does Coke sell these companies? They're making money. And he said, making money isn't the only piece. You have to look at the rate of growth. And he gave this example, the one I'm showing you right here. He said, in this case, we made $1 more profit going from 2011 to 2012. Now, if this was going to be a consistent pattern, he said in some cases it may be better for us to sell a company and put that money in the bank account. And a bank account for like Coke makes a lot more than a checking account for everybody else. Put into a bank account, and we can make more money with the interest by doing nothing than we could have by actually trying to make money. And or you could even sell the company, liquidate all the assets, and put that money in the bank account, and again make more money. So the rate of growth is an important piece. It isn't the only piece, but it's an important piece to look at. And that's what the M gives us, change in Y over change in X. And that's why I don't really like the rise and run concept, because it gets you thinking in terms of distance, and it's much more than that. Now we got a formula for the slope. If we're given 2 points, x1, y1, and x2, y2, then your slope is going to be y2 minus y1 over x2 minus x1. For example, let's say we want to find the slope of the line segment passing through -3, 1, and 4, actually let me put that as -4. -4, -5. Well, first off, we need to label them. This is our first point, so this will be x1, y1. This is our second point, so this will be x2, y2. Now, it's always a good idea, unless you don't mess up on signs at all, but it's always a good idea to go through and replace all of your variables with parentheses before you plug in your numbers. So I'm just replacing x1, y1, x2, y2 with parentheses. So now we said y2 is -5, so we'll put -5 in where the y2 is in our formula. y1 we said is 1, so I'll put a 1 in there. x2 is -4, and x1 is -3. Now let me double check that I put everything in the right spot. Okay. So we got -5 minus 1. Those parentheses aren't doing anything. We got -4, but these parentheses are. Here we got a negative parentheses negative. And remember, that's one of our shortcuts, and that becomes a positive. So then we got -5, -1 is -6. -4 plus 3 is -1, which gives us negative divided by negative is positive. So that gives us 6 as our slope. So that's how you find the slope given 2 points. Now in some cases, if you're looking at a scatter diagram, and they refer to that in the book, scatter diagram is just plotting points. If I'm plotting points, and you got something that looks like this, more or less looks like a line, and you're trying to find the slope that best represents how these points are progressing, what you do is you pick 2 points you think that might represent. Now, if you look at these 2 points here, if I draw a line through them, that's not going to be very representative of the rest of these points. So, but if I pick maybe this point and this point, well, that might not be too bad. If I draw a line through them, then that'll represent. Now, maybe this one might be better, but you try to pick 2 points that best represents it. And then if you have those 2 points, you can plug them into your slope formula and find out what the slope is of this progression. Now you might say, well, what good is that? You know, you find this magical number of 6. Well, if this was, let's say this was sales here, and this was years here, our time. Finding what this slope is, let's say that m is equal to 1200. Then this would represent, remember what the slope is, change in y over change in x. We said earlier this is our y-axis, and we said this is our x-axis. So in this case, m is equal to the change in y over the change in x. You just simply replace the y and x with what you're given in the problem. So this would say the change in sales over the change in years. So the interpretation of this 1200 is we'd say the sales is increasing $1,200 per year. So the slope actually becomes meaningful when we look at application problems. Now that's our slope. Now let's talk about our slope-intercept form. Let me clear this off. So slope, intercept, form. You'll see this written different ways in different books. Some will say m is equal to, or y is equal to mx plus b. Now if you got it in this form, m is your slope, and b is your y-intercept. That's where the slope-intercept form name comes from. Now slope-intercept form means you have y by itself. These are both the first power, and you specifically have a number in front of the x, and then you have a number over here. Now I say different books have this written in different ways. Instead of writing it that way, some books will say f of x is equal to mx plus b. Now this is using our function notation. This would be a linear function. It's still the same idea. It doesn't remember because these are interchangeable. Whether you put y there or f of x there, it's the same concept. So the m you see here is still our slope. And the b you see here is still our y-intercept. For example, if I had y is equal to 5x minus 3, since this is in slope-intercept form, y is by itself, and we got everything's the first power, then whatever number's in front of our x is our slope. So your slope is 5. And whatever number's here at the end is your y-intercept. So your y-intercept is negative 3. So we're going to have m is equal to 5. And remember your y-intercept would be 0, comma, negative 3, because the x is always equal to 0. Now sometimes you have to work to get it into the right form. For example, if we had 5x plus 2y is equal to 8, and I ask you to identify the slope and y-intercept. Well, easy way to do that is you need to solve for y. Well, in figuring out what to do, you always do the opposite operation. So I want to get y by itself, so I can subtract 5x from both sides. (5x minus 5x drops away. We got 2y equals 8 minus 5x. And then the opposite operation here, we got 2 times y. We'll divide everything by 2. When I say everything, I'm talking about what's separated by pluses, minuses, and equals. Now that's going to give us y is equal to 4 minus 5/2 x. Now sometimes you have to rewrite this into slope-intercept form. Slope-intercept form means you have to have this reversed. So we'll put the negative 5/2 x first plus 4. You can freely rearrange terms. You just have to make sure that you take the sign with it. And now once it's in this form, then whatever number's in front of your x is your slope. So m is equal to negative 5/2. And whatever number's here at the end is your y-intercept. So your y-intercept is equal to 4. Now we're going to see in a little bit, well, what's a benefit of, besides being able to identify the slope and y-intercept, where would you use that at? Let's talk about graphing. Graphing linear equations using a point and a slope. So graphing linear equations using a point and a slope. Now our first step would be to plot the point on the coordinate system. That's our x and y coordinate system. There's other coordinate systems besides x and y, but that's all we're seeing in this class. I'll grab a drink real quick here. Then, from that point, use the slope to find the second point. And I'm going to specifically show that over when we're doing the example. And then 3, draw a line through the points. Okay. Let me clear this off. And we want to graph the line. given the following conditions. It passes through the point 1, 2. And the slope is negative 1 over 2. Okay, so step 1, plot the point on the coordinate system. So we got 1, 2. And let me try that again. So 1, 2 would be right there. That's step 1. Now step 2 says from that point use a slope to find the second point. Well, our slope was negative 1 over 2. Now remember, this is the change in y over the change in x. Now if this is a if we got m, if we got a positive number up on top, then that means we're going to go up. If we got a negative number on top, that means we're going to go down. Now on the bottom, if you got a positive number, that means you're going to go right. If you got a negative number, that means you're going to go left. So what this slope actually says, it's a negative number on top here. So a negative says we go down. So that negative 1 says down 1. Now this is a positive 2 down here. Positive says we go right. So that means we're going to go right 2. So from that point, use the slope to find the second point. So we said from this point, we're going to go down 1, right 2. So we go down 1 unit, and then we go right 2 units. And that's where we'll put our second point. Then draw a line through the points. So after you get your second point, you draw a straight line through them. And as straight as I can draw it. And that would be our line. Now let me show another example of that. I won't write all the instructions out again. I'll just give the point and the slope. If we got the point, let's see, negative 2, 3, and our slope is negative 4. Plot the point on the coordinate system. So we got negative 2, 3. Would be right there. Now our slope. Our slope is negative 4, but we always want this in fraction form. Well, you can always create a fraction by always putting it over 1. Now if I scroll up a little bit, using this chart I gave you, negative up on top. Negative up in the numerator says we're going to go down. So this is down 4. And this is a positive 1. Positive says we're going to go right. So that says right 1. So from where we just drew that point, we're going to go down 4 and right 1. So down 4, 1, 2, 3, down 4 units, and right 1, and that would be where our second point goes. And then we draw a line, a straight line through them. And that would be our answer. Now that's graphing a linear equation using a point and a slope. Now the next topic is if you want to graph a linear equation using slope-intercept form. Building a t-chart is kind of tedious when you're working with lines. If you can get it in slope-intercept form, you'll find it much easier to sketch a line than it will be to plot those points. And that's what this is specifically looking at. Let me clear that off. And this example would be where we want to graph something like 2y plus 4x equals 2. So we want to graph that. And specifically, we want to graph it using slope-intercept form. So graphing a line using the slope-intercept form. Now step 1. If necessary, rewrite the problem in slope-intercept form. Because remember, slope-intercept form means you have y equals, so you have to get y by itself. Step 2, identify the slope, the number in front of the x, and the y-intercept, the number at the end. The number in front of our x is referred to as a coefficient. Now, once we get down here, then we're going to find that these instructions here are the same. So we're going to plot the y-intercept on the coordinate system. I'm going to copy this. So we're going to, on step 3, plot the y-intercept. And then, step 4, from that point, use the slope to find the second point. And then in step 5, you draw a line through the points. And again, I'll save this just like before, and make sure you get a copy of this. Okay. Now this is the main way. If you're trying to graph a linear, this is the best method to use, unless you're using technology. Okay, step 1. If necessary, rewrite the problem in slope-intercept form. So we need to get y by itself. This is step 1. So I got 2y plus 4x minus 4x is equal to negative 4x plus 2. So we're subtracting 4x from both sides. 4x minus 4x cancels, and that gives us negative 4x plus 2. And then we always do the opposite operation. Here was a plus, an adding 4x. So here we had a subtracting 4x. And it doesn't matter whether you put the 2 minus 4x like the first example I showed you earlier, or whether you put it in front. It's the same idea. Now the opposite operation here is division, because this is 2 times y. So we'll divide everything by 2. Now specifically, you want to divide these separately, so it's in slope-intercept form. So those 2's cancel, and we got y is equal to negative 2x plus 1. Now step 2, identify the slope. This is the number in front of the x. So our slope is going to be negative 2. And our y and the y-intercept, number at the end. The y-intercept will be 1. Step 3, we want to plot the y-intercept. We said the y-intercept was 1. So I go to 1 on my y-axis and I put a point. Step 4, from that point, use the slope to find the second point. So we got m is equal to negative 2 over 1. Remember, you always want it in fraction form. If it's not in fraction form, you can put it over 1. And this will be the change in y over the change in x. Now we said if you have a negative number up on top, then that means down. So this says down 2. And if you have a positive number down here, then that means right. So that means right 1. So from right 1, from our y-intercept, we're going to go down 2, right 1. So down 2 and right 1. And usually you visualize this. You don't have to draw those like you're seeing me draw it. And then step 5, draw a line through the points. So draw a line through the points. Yeah, should be a straight line. And that'll be our graph. Again, much easier to work with in that manner than it is to build one of those T-charts. Now let's take a look at graphing linear equations using the TA3, TA4. Clear that off. And it's not required that you have a TA3, TA4, but the book refers to it, so I'm going to show it. If we want to graph y is equal to 5x minus 2, it's, the only time you can put anything into your graphing calculator is when you have y by itself. So to graph these, on my calculator, I'm going to go to my y equals, and you can see it in red here. So there's my y equals. Now press clear. Clear or clear out whatever's in that line. I didn't have anything there, but if I did, it would have cleared it out. And then we put 5x minus 2. So I press my 5, and here's where the x key is. It looks like xt theta little n, and that simply puts an x on your calculator. And then minus 2. And then at that point, you press graph, and that'll give you your line. So nothing else. The graphing calculator is nice to double check when you've done it by hand to see if you got the right graph. Now we're going to take a look at now finding the equation of a line given 2 points. Example this says, and whenever it says find the equation of the line, we're always talking the slope-intercept form. So find the equation of the line given, and this is assuming, I'm not going to write out all the words, but this is assuming that it passes through this point right here, these 2 points. So the line that passes through these 2 points, we want to come up with the slope-intercept form. Well, our finding equation line our first step is to find m. Our second step is to plug in m from step 1 and the given point for x and y into y equals mx plus b and solve for b. And then step 3 is to write our answer down. We'll plug in m from step 1 and b from step 2 into y equals mx plus b. So these are the steps we're going to go through. And some problems you may find m's given to you. If you look in the textbook, there might be some problems where they give you m directly. So that first step is easy. Okay, step 1. Find m. Well, we looked at a formula earlier where if you're given 2 points, you can find out what m is. The formula was m is equal to y2 minus y1 over x2 minus x1. Now I want to label these points. This is my first point, so I'll label this as x1, y1. This is my second point, so I'll label this as x2, y2. Remember earlier I said that you should always put parentheses in before you plug in your numbers. Sometimes it helps you, sometimes it doesn't do anything, but it helps reduce sign errors. Now y2 we said was negative 2 minus y1, which we said was 1. x2 is negative 5 and x1 is 3. Negative 2, negative 1 gives us negative 3. And negative 5, negative 3 gives us negative 8. Now remember, a negative divided by negative gives you a positive, so that becomes m is equal to 3/8. Now step 2. Plug in m from step 1. We just said m was 3/8. And a given point for x and y. When they give us a point, they're giving us a specific instance of x and y. And it doesn't matter which one you pick whichever one looks easier to you. Well, the 3, 1 doesn't seem to have as many negatives. So I'm going to plug this 3 in for this x, and I'll plug 1 in for the y. So we'll plug 1 in for y, and we'll plug 3 in for x plus b. And then we want to solve for b. 3 times 3 gives us 9/8. Take the 9/8 over to the left side, and we got 1 minus 9/8 is equal to b. Now this is a mixed number form, so I can take 1 times 8, which is 8, plus a negative 9, which gives us negative 1 over 8. Now that's the same concept as when we simplified 3.5 earlier. You took 3 times 2 is 6, plus 1 is 7. So again, we took 1 times 8 is 8, plus negative 9 gives us negative 1. Cannot forget step 3. We haven't wrote down our answer yet. So step 3 says to plug in m from step 1. We said m was 3/8. So we got y is equal to 3/8 x. And then plug in b from step 2, which we said was negative 1/8. And that would be our answer. And that's in slope-intercept form. Now we also got some oddball cases of a line. So let me talk about those. Let me clear this off.
Hey, Mr. Hayes.
Yes.
I'm sorry. Could you go back? I just wanted to finish copying that third step for.
Oh yeah.
Finding. Yeah, I got a little. Yeah, that's it right there.
And while you're copying that down, I'll tell a story. Most books will talk about slope-intercept form, and they'll talk about point-slope form. And the only form I actually ever work with is the slope-intercept form. I used to show both forms when I was teaching algebra. And I had two students from Japan one semester. It was a 3-hour class. And the guy, he would pay attention during class. The girl, she didn't pay attention so much. And he would pay attention. And I asked him one night, why he was paying attention. So I was curious. And he said from his part of Japan, he couldn't come to class and not pay attention. Both of them had taken up through Calc 2, Calc 3 in high schools. And they could easily have been teaching the class. Well, he came up one night I covered this, and he said, why do you cover both forms? And I said, well, you needed both forms depending upon what the problem looked like. And he proceeded to prove to me I was wrong. He showed me that you can do 100% of the problems with the slope-intercept form. And I like that. If I got one formula that worked 100% of the time, then that's what I go with. So that's why you won't see me show an example of the point-slope form. But if you like it and you want to use it, then that's fine.
I got it copied down. Thank you.
Okay. Now our oddball cases. What identifies an oddball case is you only have one of the variables, either x or y. They'll realize we can put any variable in instead of x and y. You could have c for cost, p for profit, t for time, and so forth. Now if you have the x is equal to a number, then this is going to be a vertical line at that number. If you got y is equal to a number, this is going to be a horizontal line at that number. Now these oddball cases do not work out well if you try to apply the steps I give you up above. You just have to recognize that they're oddball cases and then sketch a graph from there. For example, if I have x is equal to 3 for a problem, I want to graph it. If you try to go through the steps I gave you, any of them, none of them will work. But this is an oddball case because there's only one of the variables. And we said if we have x is equal to a number, it's going to be a vertical line at that number. So I'm going to go to where my x is equal to 3, and I draw a vertical line. And that'd be our graph. On the other hand, if we got y is equal to 2, again, it's an oddball case, but it's only got one of the variables. That tells us y is equal to a number, tells us it's going to be a horizontal line at that number. So I go to 2 on my y-axis, and I draw a horizontal line. Now if they were asking you about the slope, if you got a vertical line, your slope is always undefined. If they give you a horizontal line, then your slope is always equal to 0. So again, those do not fit in well with finding intercepts, necessarily your y-intercept and so forth. You notice that this x equals 3 doesn't even touch the y-axis, so there is no y-intercept. This one does have a y-intercept, but the slope is a little bit hard to work with. So those are our oddball cases. Now a scatter diagram is just plotting points, and we talked about that earlier. I should have had that up above where we're plotting points. And it helps us see a pattern. And I put an example out there in the discussion where I'm looking for a pattern. Let me just generally talk about that. Maybe I'm looking here at time, and this is sales. And if I just plot my points, then you have something that looks like this. And it looks like it follows a linear pattern. And this is where you can pick 2 points, like I picked that point and that point. And you can use the steps we did earlier, where you can find the equation line that passes through them. Now, why would you want to do this? Well, this is what's called a model that allows you to predict. Maybe this goes out to time is equal to 10 years. And you're wondering what's going to happen at 12 years. What's the sales going to look like? Well, since these actually follow a pattern, then you can use this line to then predict what's going to happen out here. Now, it'll never be a perfect line. You see it misses these points, and that's not the idea. When you come up with a line, you pick the best line that goes through those points. You go on and take statistics, you find a method to find the exact line with the minimal amount of error. But in algebra, we just kind of eyeball it, and you look for 2 points that looks like a good model, and go with that. Now, after you come up with your equation, let's say I come up with y is equal to x plus 7. Then to plug the 12 in, we get 12 plus 7, which gives us 19. Maybe this is in thousands. So that tells us at year 12, we're going to have 19,000 for sales. So that's the purpose of a scatter diagram. Now back to finding the equation of a line. This is finding the equation of a line given a point and a parallel line. So finding the equation of a line given a point and a parallel line. Step 1, we want to find m. Now, first sub-step within that says to write the given line in slope-intercept form. Our second sub-step says to identify the slope. Our third sub-step says parallel lines have the same slope, so m is going to equal to, and we'll talk more about that with the example. And step 2, plug in m from step 1c and a given point for x and y into y equals mx plus b and solve for b. And then step 3 is write our answer. Plug in m from step 1c and b from step 2 into y equals mx plus b. I'll give you a minute so to write that down if you're writing it down. Now I'll flip back to that as I'm working this problem. And we want to find the equation of the line passing through for 1 and parallel to y is equal to 3x minus 2. Well, our first step says to find m. Our first sub-step within that says to write the given line in slope-intercept form. Well, we're given that it's parallel to y is equal to 3x minus 2, and this one's already in slope-intercept form. The second example for the perpendicular, I'll make up one that isn't. Now our second sub-step says to identify the slope. Now the reason why we want to put it in slope-intercept form is so we can easily identify what our slope is. Remember, your slope is whatever number is in front of your x, so slope is 3. Now our third sub-step. Parallel lines have the same slope, so m is equal to. Now we said that it's parallel to this line. We said the slope of that line is 3, and we said parallel lines have the same slope, so the m we're trying to find will be 3. Now this may be part of another problem. I remember seeing this in some of the problems out of the book, is where they'll give you a slope and then they'll ask you to find or they'll give you an equation like y is equal to 3x minus 2, and they'll ask you to find the slope of a line parallel to that. And so they're just asking you to find this piece right here. Now here we're going through the entire process. We're trying to find the equation of the line. So step 2, plug in m from step 1c. Well, we said m was 3. And a given point for x and y. Remember, when you're given a point, we're given a specific instance of x and y. So we're going to plug 1 in for y, and we'll plug 4 in for x. And then we want to solve for b. 3 times 4 is 12. Take the 12 over, and we got 1 minus 12. And we get b is equal to negative 11. But we can't forget step 3. Step 3 is to actually write our answer down. We're going to plug in m. Correct that on your document if you wrote that down. That should be plug in m from step 1c and b from step 2. Okay, so we said m back in step 1c was 3. And plug in b from step 2. B from step 2 is negative 11. So our answer will be y is equal to 3x minus 11. And that's how you find the equation of a line passing through a point and parallel to another line. Now let's take a look at finding an equation of a line passing through a point and perpendicular to another line. So finding the equation of a line passing through a point and given a perpendicular line. I'm leaving out some wording and so forth, but I'm trying to keep it fairly short. So given a perpendicular, let me write that out, line. Now step 1, we want to find m. Our first sub-step says to write the given line in slope-intercept form. Now our second sub-step says to identify the slope and our third sub-step says perpendicular lines have slopes that are negative reciprocals. So m is going to equal to, and we'll address that with the example. Step 2, plug in m from step 1c and the given point for x and y into y equals mx plus b and solve for b. And step 3, we have to write our answer down. So plug in m from step 1c and b from step 2 into y equals mx plus b. Now that probably looks familiar. That's the exact same steps I've wrote down for the couple other processes. You go on to take calculus, that's the same steps you see in calculus. The only thing that changes is how you find your slope. I'll give you a minute or so to write that down if you're writing it down. Okay, let me make up a problem dealing with that, and we'll go through those steps. Well, assuming there I am. Okay, so find the equation line passing through -2, -1, and perpendicular to 5x plus 2y is equal to 3. Step 1, find m. We want to write the given line in slope-intercept form as our first substep. So we got 5x plus 2y is equal to 3. Now slope-intercept form means we need to solve for y, so we need to get y by itself. Now I've shown the steps earlier, so this one I'll just take the 5x to the right side. Anytime you take anything across your equals, the sign changes, so the positive 5x becomes a negative 5x. And then we'll divide everything by 2. And that'll give us y is equal to negative 5/2 x plus 3/2. Now B, identify the slope. The reason why we put it in slope-intercept form is we can easily identify where the slope is. Slope is equal to negative 5/2. It'll always be whatever number's in front of your x. Now C, perpendicular lines have slopes that are negative reciprocals, so m is equal to, let's see what a negative reciprocal is. We're going to start with the slope from 1b. So start with the slope from 1b, which is our negative 5/2. Then we want to write that in fraction form. So I'll write in fraction form. Now this one's already in fraction form, so I didn't have to do anything. But if you had, for example, like a 5, if your slope was 5, you could put the 5 over 1. Remember, you can always create a fraction by putting it over 1. And then we're going to flip it. Top goes to the bottom, bottom goes to the top. This is the reciprocal part. Reciprocal means fraction flipped. Your numerator and denominator swap. And then we're going to change its sign. So it goes from a negative 2/5 to a positive 2/5. Now once you get comfortable with it, it's fairly straightforward. You take your slope, you take a reciprocal of it, you flip it, change the sign. So the m we're trying to find is going to be positive 2/5, whatever number's over here. Step 2. Plug in m from step 1c. We just said m was 2/5. So I'll put 2/5 in for the x. And a given point for x and y. Again, when they give us a point, they're giving us a specific instance of x and y. So I'll put negative 1 in for the y. And I'll put negative 2 in for the x. And then plus b. And then we want to solve for b. So we got negative 1 is equal to 2 times negative 2 is negative 4. So we got negative 4/5 plus b. Take negative 4/5 over to the left side and becomes a positive 4/5. And this is again a mixed number form. So if you take your negative 1 times 5, that gives you negative 5 plus 4 gives you your negative 1 over 5. Step 3. We want to write our answer. We want to plug in m from step 1c, which we said was 2/5. So we got y is equal to 2/5 x. And then the b from step 2, which we said was negative 1/5. So our answer will be y is equal to 2/5 x minus 1/5. And that's how you find the equation line given a point and a perpendicular line. Now again, some of the problems I noticed in the work just involved giving you a slope and then asking you what the what slope is for a line that's perpendicular to it. So you just do a little piece of it. But this shows you the entire process. Now that was this one. I didn't highlight it, but that was finding the equation of a line given a point and a perpendicular line. Now our last topic is graphing inequalities in two variables. So let me go ahead and scroll up and clear that off. This is where I'd have like y is greater than negative 1/5 x plus 2. Inequality in two variables means we have an x and a y. And we want to graph this. So graphing a linear inequality in two variables. One is pretend the inequality symbol is an equals and graph it. And along with that is if we got a less than or greater than, it's going to be a dotted line. If we have a less than or equal to or greater than or equal to, it's going to be a solid line. Then step 2, pick a test case, any point, and plug it into your original inequality. If the inequality is true, then shade the side where the point falls. If the inequality is false, shade the other side. If you're writing those down, I'll give you a minute. Okay, let's take a look at this problem. Now we said step 1. We want to pretend inequality symbols and equals and graph it. So you pretend your problem looks like this. Y is equal to negative 1/5 x plus 2. Now remember, our slope is equal to negative 1/5, and our y-intercept is equal to 2. Now negative 1 tells us we're going to go down. I think I live next to the train yard the way it goes. It says we're going to go down 1, because that's a negative. And this says we're going to go right 5. So for my y-intercept, it's at 2, so I'll go put a point at it. Then I'm going to go down 1, right 5. Now, when I'm graphing these, oftentimes I don't go through and put my tick marks everywhere. I just put the ones I need. And that really helps me to eyeball where it should be. So down 1 and right 5 would be right here. And that's because I put 5 units here to handle going right 5. Now this is a greater than, and we said a greater than is a dotted line, which means the line you're going to draw through this is going to be a dotted line. So look like that. Now I say pick a test case, any point, and plug in your original inequality. Now it does not matter what point you pick. You can pick any point on this. Usually your best one for your test case, if you can pick it, will be your origin. Your origin is where they intersect, this right here. So that, let me actually put that in a different color. So that's going to be our test case right there. And we're going to plug that into our original inequality. And this is x and this is y. So I got 0 is greater than negative 1/5 times 0 plus 2. And this is a question mark at this point. We're wondering if that's true. Well, negative 1/5 times 0 is 0. So we get, that drops away and we get 0 is greater than 2. Well, 0 is not greater than 2. This is false. Now, if the inequality is true, then it says you shade the side where the point falls. So if this came out as true, like if we had like 5 is greater than 2, that'd be true. Then we'd shade this side. But since if the inequality is false, you shade the other side. So we would shade this over here. And that'd give us our answer. Now this represents an infinite number of answers. It means there's an infinite number of x and y values that fall over here that cause this inequality to be true. Now that's the last topic I had. What questions were there?
So real quick, I think I was writing a bunch of stuff down when you started this problem. So could you show me how you got the points one more time, just on this one, on the graph?
You would let me get back there. When you get ready to do your test case, let me choose a different one just to demonstrate it. It does not matter which one you pick, but you don't want to pick one that falls on this line. So like if I picked 3, 5, 1, 2, 3, 4, 5, 3, 5, here's 3, and 5 would be up here. So it'd definitely be on this side. So this time I'd pick 3, 5. And it doesn't matter what you pick, it'll work out. Now we're going to plug that back into our original inequality. And this will be our x, remember, and this is our y. So we'll put 5 in for the y. It's greater than negative 1/5 times x, that's 3, plus 2. And this is a question mark at this point. We're not stating it's greater, we're checking to see if it's greater. So then we got negative 3/5 plus 2. Now this right here, if I put it into decimal form, and I'm not very good at decimals, I shouldn't have to plug that in. I think it's I don't know. Let's see, negative 3/5 plus 2 gives us 1.4. Now you ask yourself, once you've simplified it, if this is true or not. Well, 5 is greater than 1.4, so this would be true. So then, if the inequality is true, you shade the side where the point falls. Point falls on this side, so we'd shade this side. So if you, in response to your question, how did I get the point? I just picked any point. Now your origin is oftentimes your easiest one because it just causes everything to drop away when you plug zeros in. Does that make sense?
Yeah, I think the part that's confusing me is so if they ask you a question on the quiz or the test,
Mm-hmm.
and you start making, like you said, you just showed two different test cases, one with the 0, 0, and one with the 3, 5, and you both came out with two opposite answers. Is that going to affect what they're going to ask us? Because you can, depending on what you pick, it can be different.
I think one thing you may need to know is they'll give you a test case. If they ask you to graph it, you can pick whatever you want. But they may give you a test case, like they may give you 2-1, and they'll ask you if it's a solution. And what you do then is you plug it in. So you plug it in up here. This is our x and this is our y. So we plug 1 in for the y. You plug 2 in for the x. And then you go through and check that. And again, this is a question mark at this point. We're wondering if it's a solution. So we're wondering if that's true. So we got negative 1/5 times 2 gives us negative 2/5 plus 2. And I really am not very good with decimals. Let me plug that in. Negative 2/5 plus 2 would give us 1.6. And then you see that 1 is not greater than 1.6, is it? So this is false, which means, is this a solution? The answer would be no. If it came out with something that was true, like you had 2 is greater than 1.6, then your answer would be yes. So I've seen that in some of the problems where they'll just ask you specifically about a point.
Okay, that makes sense. Thank you.
Mm-hmm. What other questions?
I think I'm good.
Okay.
Yeah, I think I'm good too. Appreciate all the help.
Okay, well, I'll save this YouTube video, and it takes a while to upload and for YouTube process, so it won't be ready until tomorrow morning. But then I'll also send out that Word document. So, well, have a good night.
All right, you too. Thank you.
Thank you. Good night.